Hello, this is Professor Dan Kernler of Elgin Community College. This is another video in my statistics series, and this video is all about position. How does an individual compare to the population? All right, let's get started. So we're going to start with an illustrative example. Suppose we have a couple of different pairs of jeans that are on sale, and we want to know relatively which one is a better deal. Well, let's put them on a scale. We have the Levi's jeans is $34.99. The Calvin Klein is on sale for $54.99. Let's suppose that the average Levi's price is $43.12. The average Calvin Klein is $63.44. So we could certainly look at the difference from the mean. So Levi's $8.13, Calvin Klein $8.45. But there could be more to it. Let's dive in a little bit deeper and focus just on that difference from the mean. Suppose they have a different spread. Say the standard deviation of Levi's, $5.12, Calvin Klein, $9.90. So now, if we say, well, how many standard deviations are they below the mean? It looks like the Levi's one is about 1.6 standard deviations below the mean, where the Calvin Klein is only 9/10 of a standard deviation. This is the first measure of position we're going to talk about, and it's the number of standard deviations from the mean. All right, let's dive in a little bit more and talk about how this is calculated and then maybe get some symbols in here. So you take the original price, $34.99, subtract the mean, $43.12, or in the case of Calvin Klein, it's $54.99 minus the mean, $63.44. Right, then you subtract those. That gets you the negative 813, the negative 845. It's below, so they're subtracted. Then we're going to divide by the standard deviation, and that gets us this negative 1.6 or negative 9/10. That's the number of standard deviations that they are below the mean. Okay, if we look at these calculations, that $34.99 and the $54.99, those are the original prices. Let's call those X. And then the $43.12, the $63.44, those are the means, the sample means. We have our notation for that. We know it's X bar. And then the denominator, we have the standard deviations. Those are the standard deviation, S. And that gets us the number of standard deviations, negative 1.6 and negative 0.9. Let's focus on that X minus X bar over S. We're going to call this the Z-score, Z. For the sample, it would be X minus X bar over S. If you happen to have population information and you have those parameters, the mean mu and the population standard deviation sigma, then it's X minus the population mean mu over the population standard deviation sigma. In both cases, what this gives you is the number of standard deviations from the mean. This is really important. The Z-score gives you the number of standard deviations from the mean. So I have the mean and standard deviation of the age individuals realize their sexual orientation from our lesbian, gay, bisexual database. I'll put the link in the description. And these are grouped by the orientation. And let's just limit it, not look at all of them. Let's just look at bisexual, gay, and lesbian. Those are the largest sample sizes within there. Suppose we have someone who's age 19, and we want to know, well, what's their Z-score depending on which group they're in. So if it's a bisexual individual, we take that 19 minus the mean, 17.1, divide by the standard deviation, 6.9, we get about 0.28. So they're about 0.28 standard deviations above the mean if they're bisexual. For gay individuals, we do the same thing. 19 minus, in this case, a much lower mean, 14.7, divide by 5.9, the standard deviation, and we get 0.73 standard deviations above the mean. And similarly for lesbian, we subtract and divide by the standard deviation, we get about 0.24. So let's see what this looks like on a visual. So I've got the Z-scores here, and let's get the histograms up for all of these. Here's our 19, the 19 for all three of those different sexual orientations. And if we put the mean up for each of them, so the mean for bisexual, 17.1, that's so our value is 0.28 standard deviations above that. For those who are gay, the mean is 14.7, and so that's 0.73 standard deviations above the mean, the 19 is. And then for lesbian, the mean is 17.3, and so our observation is 0.24 standard deviations above the mean. Let's talk about how z-scores can be used, sometimes for good, sometimes not appropriately. One of the common ways that z-scores are used is norming, comparing an individual to its population. So you might say, well, is this speed a fast speed in a race? Well, are we talking about 10-year-olds? Are we talking about 20-year-olds? Are we talking about local high school race? Or are we talking about the Olympics? So you norm to the population. But there are some downsides to this. One example I found of how this z-scores can be used is in a school district. This particular school district was using it to determine who was qualified for the gifted program. So they would look at these different scores on these different tests, and then they would calculate the different z-scores and then use those z-scores to see if someone was qualified. The problem is we know that testing is associated with income levels, and so you're norming it just to, look, who are you comparing it to? If you're just comparing it to by age, then there are problems with that necessarily determining that someone is gifted simply because of a test score. Another common norming issue is using race to norm things. There are some researchers that have found that without using race or ethnicity in a clinical setting, then some groups, particularly African Americans, might get incorrectly classified, like overclassified as having some impairment. The problem here, and the researchers even acknowledge this, is there's multiple background differences, there's different educational experiences, and it's not like race is a causal variable. It's just a proxy for some of these other things. And they've got a list of them here: academic exposure, educational quality, resources, acculturation, socioeconomic status, social exposure, test wiseness, discrimination, all of these things. But yet, if you don't have a measure of all of those things in your database, and you know the individual's race or ethnicity, they can use race or ethnicity as a proxy for those other things, and it helps get a more accurate diagnosis. But there are significant downsides. Here's another research study, and they have this long list of different tests that use race and adjust for race, but then there are these concerns that pop up. Here's one. If you do this race correction, what happens is it raises the threshold for what a black patient might need to do to be qualified for this particular therapy. Here's another one. Using this tool limits the number of African American kidney donors. Here's another one. If they use the race or ethnicity to determine if someone has a likelihood of survival, if they use that, then in the model, Black or African Americans look less likely, so they might be less likely to get interventions. Here's another one. Again, this lower risk reported for non-white women might delay their intervention for this particular therapy because the model says, well, on average, according to our model, this predicts that they're lower risk. And there is a long laundry list of different interventions that have this possible kind of unintended consequence of using race as a proxy for all these other variables. Even though it might work well in the model, there's all these misdiagnoses that happen because they use that particular variable and norm according with that variable. Another example that's come up in the news lately is with the NFL and players qualifying for benefits from the league if they have dementia at a much earlier age than they otherwise would. But the model uses two different scales. It points to what we talked about earlier, where they're adjusting for race or ethnicity. The problem is it was intended to avoid misdiagnoses, but the end result is now Black players have to show a steeper decline in their cognitive ability in order to qualify. Okay, so our first measure of position was z-score. Let's talk about our second one. You have probably seen this one already. I've got a fake SAT report here. If we zoom in, you can see there are the scores, the original scores on the test, but then there's also these percentiles. So the percentile is the next thing we're going to talk about. Let's focus on this, say we're the 44th nationally representative sample percentile. So SAT scores vary from 200 to 800 on the individual tests. 44th mean that there's 44% less. That's what the 44th percentile means. There's 44% below that observation. And one thing you might wonder is there was another percentile. There was a 35th with SA user percentile. Well, if we go back to the main report, over on the right, kind of zooming in there, the national representative sample was how your percentile compares to representative of all students. And then the SAT user is of those who actually took the test, what's your percentile? Let's talk about finding percentiles in Statcrunch. So we're still in our lesbian, gay, bisexual database. I'll put that link in the description again. So we're looking at the age realized variable. So we'll do summary stats columns, scroll down, click that variable. And then down in one of the statistics, you can see, you can actually just type in, let's do the 60th percentile here. And you can see that 60th percentile is about 16. The other thing you might want to do is, well, suppose we have an individual who realized that they were their particular sexual orientation at age 20. And so the question is, well, what percentile is that particular age? What we need then is we need to know what percent are up to that particular age. We need to do a table, and we need the cumulative relative frequency. So we're going to do stat tables frequency and do cumulative relative frequency. And when you hit compute here, you gotta be careful. There is a bunch of values from a young age all the way to an old age, and it wants to group them, which is good. It wants to group them, but we need them still individual. So what we're gonna do then is actually hit cancel on that, don't bin them. And then we're going to scroll down, find our particular age, and we can see it's about 86%. So 86% are up to and including an age of 20. So 20 would be about the 86th percentile. It's worth noting that there is no universal definition of percentile. Some definitions include that value, some do not. So some might describe it as the 82nd percentile, looking at 19 and below. So there are 82% below age 20, 86% up to and including age 20. All right, next topic. In addition to percentiles, there are specific percentiles at the quarters called quartiles. So if we look at, say we have the interval of our data here, split it up into quarters, 25% at each. We have the minimum, we have the maximum, and then we have this first quartile. The notation for that is Q with a subscript of 1. Then we have the second quartile, which is the median, right? That's the one in the middle. And then we have the third quartile, Q3. Let's look at an example and find these. Let's use our 2018-2019 Illinois school data, and let's look at the SAT math scores, and let's look at the percent that are proficient. So summary stats columns, choose that particular variable. There's a lot of them here. You got to scroll down and find that one. And we just want the minimum, Q1, median, Q3, maximum. And I'm holding down the control button as I click on these. One thing that might be interesting to investigate is, well, how does this differ between students who are low income and students who are not low income? So we can go back in, options, edit, and select those additional two columns, the ones that are low income and the ones that are not low income. So if we look at the ones just overall, we have a scale here on the bottom, 0 to 100, and you can see we have this kind of breakdown for the minimum, Q1, median, Q3, maximum. If we add in the low income and non-low income, well, we have this overall here, and then we have the low income and non-low income. And this, if you look very carefully, you should see something that is really pronounced. They have pretty similar maximums. So this is at schools. What's the percent of students who are proficient on the SAT at the individual schools? So those two maximums are pretty similar, above 90%. If you look at the middle 50% though, very different. So this is the distribution of scores of students who are not low income versus those who are low income. And that's one trend we will see in a variety of different investigations, that students who are low income tend to score lower on these tests. They're certainly not less intelligent. They just have additional barriers. This isn't necessarily about the schools being bad or not bad. This is at the same school, right? So this is measuring at that school, what percent of the students who are non-low income are proficient and what percent of the students who are low income are proficient. So it's not the percent that are proficient at that school. That's the bottom one. That's the overall, but it's splitting it up. And so even at the same school, there's a different distribution for the percent, for the proficiency percent for those who are low income versus those who are not. This is a really interesting societal thing, and it tells us information about why students who are low income need additional supports, not because they lack intelligence or work ethic or their families don't care or any of those things. There are just additional challenges that just boom, once you look at this data, pop out at you. You can't avoid it. It is blatantly obvious that they're just a different distribution, and so they need different supports. Let's see what this looks like on the histogram and see how we can kind of see that connection there. So if we add those two histograms, you can see the distribution is very different. If you look at that middle 50%, right in the middle there, that's between 21.1 and 46.6 for the students who are not low income. And look at the distribution for those who are low income. Much different, very concentrated, very right skewed. I mean, the non-low income are right skewed as well, but the low income students, very right skewed. And you can see that that middle 50% is much more over to the left. All right, that is it for this video. I hope you found it interesting. If you want to see more of these, subscribe, hit the bell to get notifications. There's a whole series of these coming out. I always want to thank also the Elgin Community College Board of Trustees who approved my sabbatical for the spring 2021 semester. And that's when I was able to record all of these videos. So thank you so much for watching. I hope you enjoyed it, and I will see you in the next one.